Okay. Let me start by thanking the organizer for providing me a chance to present my talk here. So thank you very much. Yes. Can you see?
Yeah. Thank you very much. Announce your title.
Okay. Just a minute. There is a problem.
Don't worry.
The title of my talk is a short note on Hurewicz and I-Hurewicz properties in topological spaces. After George Cantor proved the uncountability of the set of all real numbers using his celebrated method of diagonalization, it generated investigation in mathematics which can be simply put in the following way. Given a sequence of mathematical objects of one kind, choose some elements from each end so that the chosen elements form an object of some desired kind. For two given collections A and B, selection principles means selecting elements from A under some rule to find elements of B. Now, in 1996, Marian Schippers began a systematic study of selection principles in topology and their relations to game theory and Ramsey theory. Mainly, there are three classical selection principles. Let X be an infinite set and A and B be non-empty subset of P of Px, where Px is the power set of X. Now, these three are three classical selection principles. Can you see? Hello? Can you see and hear?
Yes. Okay.
Continue. Okay. Now, this is a brief history of the classical selection principles. Menger introduced a property in metric space, which is called Menger basis property. What is that? A metric space is said to have a Menger basis property if for each basis of the metric space there is a sequence in B such that its diameter tends to 0 and it is covered by those Bn. Now, Menger conjectured that a metric space has this basis property if and only if the space is sigma compact. Now, motivated by this conjecture, Hurewicz introduced the selection principle S2A. He proved that a metric space has basis property if and only it satisfies the selection principle S2OO, which is later defined as Menger basis property, Menger property. Now, Hurewicz also introduced the selection principle using AB and a related covering property which is nowadays called Hurewicz property. A space X has the Hurewicz property if for each sequence of open covers of X there is a sequence Bn such that for each n, Bn is a finite subset of Un and each element of the space belongs to all but finitely many union Bn. Now, Hurewicz conjecture that a non-compact metric space is sigma compact if and only if it has the Hurewicz property. In 1938. Hello? Hello? Hello, can you hear me?
Hello. Sorry, please, excuse me, Dr. Michalak, turn off, if you pleasure, your microphone.
Sorry.
Turn off, please. Excuse me.
Hello?
You can continue, Samantha.
Okay. Just a minute. Okay. In 1938, Rothberger introduced a selection principle named S1AB. Actually, the motivation behind the introduction of the selection principle was a conjecture by Borel. And Rothberger observed that if a metric space has the property S100, then it has Borel strong measure 0. However, the converse is not true. And the property S100 is called Rothberger property, where O is the collection of all open sets of the metric space X, D. The classical selection principles, all the selection principles are mainly applied to different classes of covers. An open cover U of X is said to be an omega cover or a large cover or a gamma cover if these conditions hold. There is another type of open cover which is called a groupable cover. But the main idea behind the notion of groupability is to study that if we part an element A of which is like this, into mutually disjoint finite collection, then what kind of properties they possess after they make unions of these partitions. So these are the brief introduction of the classical selection principle and classical covers, etc. But on the other hand, the concept of ideals on a non-empty set Y is a generalization of small sets of Y, precisely finite sets. One of its beautiful applications is the introduction of ideal convergence, which is a generalization of statistical convergence. Mayo and Poshinak applied the idea of statistical convergence to open covers and properties associated with them. Thus, the statistical analogues of some kinds of open covers and selection principles were introduced using actually the ideal of asymptotic density zero sets of them. So, here a natural question arises whether one can proceed with similar investigations using arbitrary ideals instead of special types of ideals. So before going into our results, let us recall what we mean by an ideal. Let Y be a non-empty set. A family I, which is a subset of T Y, where Q is the first set of Y, is said to be an ideal on Y if it is closed under finite unions and hereditary. I is admissible if further I covers Y. The collection of all finite subset of Y is an admissible. The collection of all finite subsets of Y is an example of an admissible ideal on Y. Now, by affine, we denote the ideal of all finite subsets of Y, and henceforth we consider I an admissible proper ideal on N unless otherwise stated. Now, here are some definitions of ideal variant of classical covers which were defined here. Now, what is the motivation behind the definition of this ideal variant? Actually, see that if we take I is equal to affine, then the ideal notions coincide with the classical notions. Now, what is there in this definition? An open cover, a countable one, is said to be an I gamma cover if for each X this set belongs to I. That means where X is not in UN, this set is not a very big set, but as well as it is not as small as a finite set. In this way, it generalizes the notion of the classical gamma cover. It is a bigger class than the class of all gamma covers. And also, there is a thing to be noted here, that here, see, if we change the enumeration of this cover, then we don't know that whether it will be again an I gamma cover or not. So here, the enumeration plays a very significant role. Now, certain covering properties were defined in terms of selection principles. The basic idea has old roots and goes back to the study by Cantor, Borel, Menger, etc. Now, one of the most important covering property was introduced by Hurewicz in 1925, which was called Hurewicz property, and I have shown it in this slide. Look, what is called Hurewicz property. If for each sequence of open covers of X, there is a sequence Vn such that for each n, Vn is a finite subset of Un, and each element of the space belongs to all but finitely many unions. Now, clearly, every sigma compact space is a Hurewicz space, and if a space has Hurewicz property, then it is Lindelof. So Hurewicz property lies in between sigma compactness and Lindelof property. And what about its ideal variant? Now, in 2013, my thesis advisor, Professor P. Dash, initiated the notion of ideal Hurewicz property, which is a generalization of the notion of Hurewicz property. And what is that? A space is said to have Hurewicz property if for each sequence of elements of O, that means each sequence of open covers of X, there is a sequence Vn such that for each n, Vn is a finite subset of Un, and this set is an AGMA cover. That means this set satisfies these conditions. Now here also, if we take I is equal to I fin, we go back to the notion of Hurewicz property. So every Hurewicz, if a space has Hurewicz property, then it has I-Hurewicz property. The aim of this study is to characterize Hurewicz and I-Hurewicz property in terms of selection principles related to different classes of open covers, mainly in terms of ideal variant of some classes of open covers, and to check roles of different types of ideals here. Now, in a paper, Poshinak and his co-authors established that if space X satisfies this selection principle, then it is sufficient that the space is Hurewicz, and also conversely. And this selection principle implies this one. So this is an weaker assumption on X. But what we find that if I is a meager ideal, then this selection principle is sufficient for the space to have Hurewicz property. So this result is stronger than this one if we take I a meager ideal. Here also we characterize Hurewicz property of a space with the help of this selection principle and taking I with the property which is called a pseudo union, which is defined here. Okay. Now, what is the significance of this theorem? It is to be noted that this selection implies this one. Why? Because this set is a subset of this set. Thus, the previous theorem gives the converse. Thus, the previous theorem, that means this one, gives the converse for the class of epsilon spaces where I has a pseudo union. Therefore, the theorem immediately suggests the following question: is there a Lindelof non-epsilon space such that this holds but this fails? Now, what we have done here, here we characterize I-Hurewicz property of a space which is zero-dimensional Lindelof, of course, in terms of its continuous images. Okay, we see that if a space has Hurewicz property, then it has I-Hurewicz property. But the question is, when is an I-Hurewicz space is Hurewicz? And here we take the help of this selection principle, and we see that if X is a epsilon space satisfying this selection principle, and if I is a meager ideal of n, if X has I-Hurewicz property, it has Hurewicz property. Now, here are some preservation results for I-Hurewicz property. What we have obtained here that I-Hurewicz property is preserved under countable unions, continuous mappings, F-sigma subsets. And in case of the product, we see that if X be a sigma compact and Y is I-Hurewicz, then their finite product, yes, of course, it has I-Hurewicz property. And if X satisfies this selection principle, and if Y have this I-Hurewicz property, then their product also has I-Hurewicz property. Here we study I-Hurewicz property of filter. Now, what is a filter? Actually, I have not defined what is called a filter. Filter is a notion dual to ideal. Okay, so let F be a filter on a countable set Y containing the Fletcher filter on. What is the Fletcher filter? Fletcher filter is the collection of all cofinite subsets of Y. If we collect all cofinite subsets of Y, then we see that it is a filter on Y. Recall that a subset B beta of a filter F on Y is said to be a base of the filter if for any element of the filter there is a B such that B subset is. And we find if a filter F has I-Hurewicz property, then every finite product also has I-Hurewicz property. And if a base of a filter has I-Hurewicz, then the filter has I-Hurewicz. The character F of a filter is the minimal cardinality of a family generating the filter. And we find if a filter F does not have I-Hurewicz property, then its character must be greater or equal to this specific cardinality. And what I have actually defined what is that. If we take two functions from n to n, and we said if and g satisfies this relation, if and only if this holds, and a subset of this space is said to be I bounded. If we find a function such that this holds for each x, and the minimal cardinality beta. What is that? It is the minimal cardinality of an unbounded subset of this. Okay, so this is beta I. And we find that if a filter F does not have I-Hurewicz property, then its character must be greater or equal to this infinite cardinality. And here we, so in previous one, what we see that if a filter does not have I-Hurewicz property, then its character must be greater or equal to this one. But here we able to construct a filter of character this one such that it does not have any I-Hurewicz property. Now here we actually the aim of this slide is to show the hereditary property, hereditary I-Hurewicz property. Now what is a hereditary property? A space is said to have hereditary P property if every subspace of X has property. But for doing so, here we do something. We take compactification, one-point compactification of M, and we then take the Tychonoff product of M. If I be an ideal on M, and if I be dual filter, so what is the dual filter? If we take an ideal which is admissible proper and of course non-trivial, and we just make complements of this of the elements of I, then what we get, it is a filter. Okay, it is a filter on the same set here N, and it is called a dual filter. An element F in here is said to be finite in filter if this set belongs to Fi. So this is a subspace of this one consisting of all functions which are finite in filter. And the partial order, in previous slides, I have shown that what is this relation. This is the relation, okay? But here is, look here, F and G is a member of this one. But if we take here this space, the this relation can be automatically extended to here. Okay, and we see that if A is a subset of this space with I-Hurewicz property, then it must be I-bounded. And here we characterize hereditary I-Hurewicz property in terms of its continuous images into this space. But here also we take X a zero-dimensional envelope space with the assumption that each G delta subset of X is F sigma. So what we have done here, what we have done in this talk is that we characterize Hurewicz and I-Hurewicz property in terms of its continuous images, in terms of different selection principles, and we check some preservation of what are the conditions under which the I-Hurewicz property is preserved, and finally we find that when space is hereditary I-Hurewicz property, that means when every subspace of a space with, of course, which is zero-dimensional and Islam space is I-Hurewicz. So that much I have done. These are some references, and the talk is mainly based on this paper of mine with Professor Dash and Professor Chandra, which was accepted in topology application in 2019. So next is the most important slide, I think. Thank you very much.